Let's look at mathematical formulation of standard deviation as a risk measure. Standard deviation, which is denoted by sigma and is calculating using this formula, essentially the square root of the expected return, the expected value of r squared minus the square of the expected value of r. Here r represents annual return, and E represents the expected value or mathematical expectation. This formula captures the essence of volatility. It measures how far individual returns deviate from the average return. The squaring process ensures that positive and negative deviations don't cancel each other out, and the square root brings the result back to the same units as the original return. When we move to portfolio analysis, the calculation becomes more complex because we must account for correlations between different assets. The portfolio variance formula incorporates not just the individual variances of each asset, but also the covariances between assets. The portfolio variance formula, which is shown here, includes the weights of each asset, the individual variances, sigma square, and the covariance term, covariance between asset A and asset B. The weights represents how much of each asset is in the portfolio, while the covariance terms capture how the assets move together. The portfolio standard deviation is then the square root of the portfolio variance. This mathematical framework allows us to quantify exactly how diversification reduces risk. When assets are not perfectly correlated, the portfolio standard deviation is less than the weighted average of individual standard deviations. In addition to understanding portfolio risk, we must also understand portfolio expected return. So portfolio expected return is simply a weighted average of the individual asset returns. The formula shows that the expected return of a portfolio equals the sum of each asset's weights times the expected return. This is mathematically straightforward, but conceptually important. Unlike risk, which can be reduced through diversification, expected return is simply the weighted average of component returns. You can't create higher expected returns through diversification alone. You can only achieve the weighted average of what you put into the portfolio. This creates an interesting asymmetry. Diversification reduces risk, the denominator is risk-adjusted return measures, without reducing expected return, which is the numerator. This is why diversification is often called the only free lunch in finance. It allows you to improve your risk-adjusted returns without giving up expected returns. Understanding this relationship is very important for portfolio optimization and explains why professional portfolio managers spend so much effort on asset allocation and correlation analysis. Moving to our next risk measure, the Sharpe ratio, which provides a different perspective on risk by focusing on risk-adjusted performance. The Sharpe ratio measures investment performance by considering associated risks. Unlike standard deviation, which only measures risks, the Sharpe ratio tells us how much return we're getting per unit of risk taking. To calculate the Sharpe ratio, we remove the risk-free rate of return from the overall expected return of an investment, then divide by the standard deviation. This gives us the excess return per unit of risk. The Sharpe ratio is most useful when evaluating different investment options because it allows us to easily understand which companies or industries generate higher returns for any given level of risk. For example, if investment A has a Sharpe ratio of 0.8 and investment B has a Sharpe ratio of 1.2, investment B provides better risk-adjusted returns. It gives more return per unit of risk. This measure is particularly valuable because it allows us to compare investments with different risk levels on an apples-to-apples basis. A high-risk investment might have a higher absolute return, but when adjusted for risk, it may actually be inferior to a lower-risk alternative. The Trainer ratio represents another variation of risk-adjusted return measurement, but it focuses specifically on systematic risk rather than total risk. The Trainer ratio integrates a portfolio's beta with market performance. While the Sharpe ratio uses standard deviation, which is total risk in the denominator, the Trevor ratio uses beta, which is systematic risk in the denominator. So this brings us to beta. This is a measure of an investment's volatility compared to the general market, specifically measuring systematic risk. So beta is crucial because it tells us how much an investment's price moves relative to market movements. Understanding beta is essential for portfolio management because it helps us understand how much market risk we're taking on. A portfolio with a high beta will be more volatile than the market, while a portfolio with a low beta will be less volatile than the market. The distinction between the Sharpe ratio and Trainer ratio reflects different philosophies about risk measurement. Should we focus on total risk, which is Sharpe, or just market-related risk, which is Trainer? Both have their place in comprehensive risk analysis. R-squared represents another important component of our risk measurement toolkit, providing insight into how much of an asset's movement can be explained by market's movements. In statistics, R-squared is a fundamental component of regression analysis, measuring the proportion of variance in the dependent variable that's explained by the independent variable. For investment purposes, R-squared measures the explained movement of a fund or security in relation to a benchmark. So the coefficient R represents the correlation between an investment and its benchmark, and R-squared tells us what percentage of the investment's movements can be attributed to market movements. A high R-squared shows that a portfolio's performance closely tracks the market risk, the market index. For example, an R-squared of 0.95 means that 95% of the portfolio's movement can be explained by market movements, while only 5% is due to other factors. When used together with beta, R-squared can provide a comprehensive picture of asset performance. A high beta with a high R-squared indicates that the asset is highly sensitive to market movement, and that this sensitivity is consistent. A high beta with a low R-squared might indicate that the asset is volatile, but its movements aren't well explained by market movements alone. The combination helps investors understand not just how risky an investment is, but also where that risk is coming from. Now let's look deeper into beta, as it's one of the most important risk measures in modern finance. Beta measures the amount of systematic risk an individual security or sector has relative to the entire stock market. It's a measure of relative volatility, how much more or less volatile an asset is compared to the overall market. The market always serves as the beta benchmark. Every investment is compared to the market, and the market always has a beta of exactly 1 by definition. Here's how to interpret beta values. If a security beta is 1, then the security has exactly the same volatility profile as the broad market. When the market goes up 10%, the security will be expected to go up 10%. When the market goes down 10%, the security will be expected to go down 10%. A security with a beta greater than 1 is more volatile than the market. If let's say a stock has a beta of 1.5, it would be expected to move 15% when the market moves 10%. It amplifies market movements, essentially. Security with a beta less than 1 is less volatile than the market. So a stock with a beta of 0.5 would be expected to move only 5% when the market moves 10%. So it dampens market movements. Understanding beta is very important for portfolio construction. If you want a conservative portfolio, you focus on low beta stocks. If you're willing to take on more risk for potentially high return, you might include high beta stocks.